Welcome to the Australasian Bayesian Network Modelling Society webinar series. Our vision is to provide practical and free information about Bayesian network modeling so that you can use this tool in what you do best. For more great content, you can follow us on Twitter, check out our website, and subscribe to our channel. Please enjoy today's webinar.
Thanks everyone for joining. Today I'm going to be presenting on behalf of the Australasian Bayesian Network Modelling Society on No Data, No Problem, looking at the versatility of Bayesian networks in different data landscapes. We're going to go through really quickly a little bit about how a basic Bayesian network models the data. Then we're going to have a look about where we can get this data from, and finally how we can integrate all this data from different sources into a single model. So Sandra Johnson already gave us a really great introduction in our first webinar, which is now up on YouTube, on how Bayesian networks model data. So just as a refresher, it's all about linking the evidence to the probability of events. So using koalas as an example, because they are adorable, say we know that the amount of habitat and the disease burden is going to affect our koala population. We also know that the amount of habitat is going to affect the disease burden on koalas. This is the exact kind of information that we put into our Bayesian networks. Just a bit of jargon to cover. It's the variables, we refer to them as nodes. And we join these nodes with links, sometimes referred to as edges. And they can represent either correlation or causality or some sort of association, depending on your model and how you interpret your model. Now, behind each of these nodes sits a conditional probability table, or CPT, and these give the probability of an event occurring given the evidence. So, for example, if we have a sustainable amount of habitat but a high disease burden, we might say there's a 25% chance that our koala population will still decline. This is the bit that we're going to drill down in today. Why 25%? Where do these numbers come from? It's like magic. Well, there's a couple of places we can get them from. We can either learn them from some data, if we're lucky enough to have some, or we can manually enter them into our CPTs and fill them out ourselves if we think we know what the answer is. So one way we can do this is we can collect some data ourselves. And here's a photo of me in Samoa diligently collecting some data for our seroprevalence survey. And as an example, I'm just going to go through the details of a similar study that we did, looking at the high-risk locations for leptospirosis in Fiji. So this was some field work that was done. There was a big survey, house to house, where we did questionnaire data. So giving everyone a survey, and also seroprevalence. So we tested blood samples to figure out whether or not there was leptospirosis infection. We sneakily complemented this with some geospatial data that we were able to get from government departments, and downloads, things like elevation in rivers and soils, livestock, census data, all of that sort of thing. Using that data, we were able to make this really fancy data set, which we can then use to populate our model. So we use this data set to actually learn the structure of a Bayesian network and to learn what those probabilities are behind each of those nodes that you see there. And this is a really nice thing about Bayesian networks. They're great for field data where you tend to have missing values. So lots of things go wrong in the field. Sometimes you don't get all the results that you want, or mishaps occur. And Bayesian networks are cool with that. It's fine. You can just work out the probabilities with what you've got. As a side note, categorical data is also no problem for a Bayesian network. So here you can see where we have urban or peri-urban. It's no problem. We just use those categories to make the states of our Bayesian networks. So But once we've used our data and we've trained our Bayesian network, we can then enter in values to get scenarios. So here we use geospatial data to set the scenarios, which allows us to create an awesome risk map. And if you don't love maps, you should, because they're such a fantastic way to get a really good picture of exactly what's happening and the details. So here we can see the predicted high-risk areas for leptospirosis. And we can also generate different maps for different scenarios, such as the predicted impact of different interventions. And so that's all well and good, but what do you do if your PhD student or postdoc doesn't want to leave the house and won't go and get some data for you? Well, it's not the end of the world, because there is loads of free data available. So here we've got some examples. We've got land use change, protected areas, ecoregions, population pressure, slope elevation, distance to rivers, roads, railroads, anything. It's all available online, it's all free, and you can do some really cool stuff with it. So here's an example from my PhD thesis looking at applying machine learning to predicting deforestation. And we use loads of free data sets to create our values. And then we use those, enter those into a Bayesian network and use them to predict the probability of an area being deforested. And you can see the results here, and they're pretty good. You can just get a pretty good picture. So never underestimate the value of free data. Sometimes, however, we don't even have that. So particularly for interdisciplinary problems or complex social problems, we often don't have any data. We can't download it. Nobody knows the answer. And then we can ask some experts. So here's an example of that. This is looking at how do policy instruments affect the adoption of eco-friendly farming practices in the Great Barrier Reef catchment, which is a mouthful, so I'll go through and explain that. We're looking at eco-friendly farming practices, so agricultural practices which reduce the risk to downstream water quality. This can be harvesting practices, limiting fertilizers like nitrogen, so there's less runoff into barrier reef, and revegetation of riparian zones along creeks. Now, there's a lot of different policy instruments that we can use to convince and try and persuade farmers to adopt these practices. We can use regulations. We can offer financial incentives like grants or credit schemes. We rely heavily on our social and behavioural scientists, so things like extension and outreach programs to go out and actually work with the farmers and help them. And we have different governance strategies we can use. So based on all of these different policy instruments, we are going to need lots of different experts. And our experts are going to need some help. So you can't just get all your experts together in a room and give them some sandwiches and a pack of Tim Tams, come back in 5 hours and expect them to have a Bayesian network for you. It's a facilitated process, it's participatory, and it needs to be structured, which is where your data modelers and your workshop facilitators come into play. So here's an example of the questionnaires we use to help our experts structure their knowledge into the right format for us to enter into the Bayesian networks. So we ask them for their lowest and highest plausible values to anchor them, so they sort of get their head in the right space. Then we ask them what's the most likely plausible value, and we also ask them their confidence, which we can take into account when calculating our final values. And you can see at the top there, the question, we put that into a scenario to help them understand it and make all of our assumptions very clear. So this is the Bayesian network they came up with, which looks terribly complicated and scary at first sight, and that's because it sort of is. But basically what it does is it looks at the characteristics of different policies, different populations, different practices, and the mechanisms behind it, and whether or not they're going to change farm adoption. The crux of it is that practice adoption is based on whether a farmer wants to adopt and whether they can adopt. This top corner here, we look at our social and behavioural sciences, so our extension programs. We have all of our regulation components in there, our different financial instruments and some things to do with them. And the take-home message here is that all of those values from all of those different areas, we populate those CPTs using the values that the experts gave us in that facilitated process. Sometimes that's not even enough though. So sometimes we need an evidence-based model. We know there's evidence there, but it's all in different places and it's in different formats. Then we just kind of need to scrounge around a bit, and that's fine too. So here's a nice COVID example for us. Let's look at how much of a risk are the AstraZeneca-related blood clots, which is reasonably topical at the moment. And Shannon is going to put the link to the preprint for this model into the chat for anyone who's interested in the details or wants to know about public health outcomes. You can follow that up there. But on the modelling side of things, which is my favourite part, this is our Bayesian network that looks at the risk of dying from atypical blood clots versus the risk of dying from COVID. Again, it answers a few different questions and you can look at it in different sections. So what is the chance of developing an atypical blood clot from either the background levels or from the AstraZeneca vaccine? Then we need to look at, well, what are your chances of actually developing symptomatic COVID? And for comparison, if you develop that symptomatic COVID, what are your chances of dying from it or from COVID-related blood clots? Now, to populate this model, we used different data from different areas. The only sort of precursor or condition was that it had to be evidence-based, and our experts had to agree on the interpretation. So here you can see, for example, for a vaccine-induced TTS, we used numbers from ATAGI, the Australian Technical Advisory Group on Immunisation, from their weekly updates. Sorry, just on that. And the second one, dying from vaccine-induced TTS, we consulted the Thrombosis and Haematosis Society for Australia and New Zealand, who currently advise the government, and got their value for that. For the background rate of clots, there's a few good international studies we can use, and we can pull the value from there. Vaccine effectiveness has to come from different sources. We can use Australian data, which is our preference. We're trying to model the risk in Australia. For our Delta strain, we can use the Doherty modelling. However, given that we had very few cases early on in the pandemic, when Alpha strain was prominent, we need to get the Alpha data. We can use UK data for that on the vaccine effectiveness against that Alpha strain. And looking at the risk of dying from COVID based on age, we can get case numbers and statistics from the Australian government website and use that information there. So that gives you just a couple of examples of different ways you can use your Bayesian networks with different data. And they fall into these sort of two broad categories. One is that where we learn the probabilities and the structure from the data. So we're really falling into that machine learning space. The others where we just sort of enter in our values, then we're looking more of what sort of knowledge synthesis, for want of a better term. And the nice thing about all of these, of course, as we know about Bayesian networks, is that they can be updated as we fill in these knowledge gaps. So, for example, if a new report comes out with monitoring for quality on the barrier reef water, or if ATAGI put out a new weekly report, which they often do, given that they're weekly reports, we can update our network for that to get the most recent current data. So this is just a few options I've come up with as examples. There's going to be loads more options. You might want to feed in data from existing systems or use outputs from modelling simulations, or there's probably loads of others I haven't thought of. The point is that Bayesian networks are fabulous and they are a versatile way to solve problems using information from a range of sources. When I use them, they tend to also become a very social affair. So there's loads of acknowledgements and people that need to be thanked. So Connell Watson and Colleen Lau, who led the Fiji study. The RP225 reef policy analysis was funded by the Office of the Great Barrier Reef. And the Coral Risk Calculator was supported by the Immunisation Coalition. And keep an eye on their website because the results of that will be out soon.